All right, in this video, we're going to take a look at some reaction stoichiometry problems with the gases unit. So sometimes these are just called gas stoichiometry problems. If you have your worksheets with you, it's on page 24 of the worksheet package you picked up in class. So there's several questions here that all deal with gas stoichiometry. Remember that stoichiometry usually involves a chemical reaction of some type, and stoichiometry means we're going to use the ratios from the balanced equation. So question 22, when heated, some sodium chlorate decomposes, and we're given an unbalanced equation. Pause the video and write down a balanced equation for yourself. So I'll put a 2 in front of the sodium chlorate to give me 6 oxygens on the left. I'll put a 3 in front of the oxygen on the right to give me 6 oxygen atoms on the right. And then a 2 in front of sodium chloride will finish balancing. Now the question says you have 5 grams, 5.00 grams of sodium chlorate decomposing, and we're asked what volume of oxygen gas would be produced at a certain temperature and a certain pressure. Now back in our stoichiometry unit, we would have asked a similar question, but it would have said that the oxygen was collected at STP, standard temperature and pressure. If it was collected at STP, then we have a unit multiplier that we can use. There's 22.4 liters of any gas in 1 mole at STP. But this is not STP, so we can't use that unit multiplier. So let's jump in and see what we can do. If I've got 5 grams of sodium chlorate, I suppose one thing I could do would be to calculate how many moles of oxygen would be produced. Then once I know the moles of oxygen, I could take the temperature and pressure and convert that to volume using the ideal gas law. So there's my plan. I'm going to find the moles of oxygen with some stoichiometry unit multipliers. Then I'll have moles. I'll do the ideal gas law to find volume. So pause the video and see if you can do that yourself. So take your 5 grams of sodium chlorate and let's convert grams to moles of sodium chlorate. And then using the balanced equation that we have above, we can convert moles of sodium chlorate to moles of oxygen, right? We're trying to find volume of oxygen, so let's get the moles of oxygen. So using the molar mass, grab a periodic table, sodium 22.99, chlorine 35.45, and 3 oxygens that reach 16. The molar mass is 106.44 grams per mole. And using the balanced equation, 3 moles of oxygen come from 2 moles of sodium chlorate. So 5 grams out of 106.44, and then times 3/2 will produce, we can keep 3 significant digits, so 0.0705 moles of oxygen gas. Now that we have the moles, we can go to the ideal gas law. PV is nRT, and we're looking for volume, so volume is nRT divided by P. We know the moles, we know the temperature, we know the pressure. We'll use the appropriate value for the ideal gas constant, R, and then we'll have the volume. So let's put our moles in, 0.0705 moles. Now, which R value should we use? Looking at the question, the pressure is given in kilopascals. If the pressure is in kilopascals, we'll use 8.314 as the value for the gas constant. The temperature has to be in Kelvin. This is 500 degrees Celsius. So if I add 273 to that, I get 773 Kelvin. And then the pressure in kilopascals, 175 kPa. We can keep 3 significant digits in our answer, 0.0705 times 8.314 times 773, and divided by 175, that's going to give me the number of number of liters, 2.59 liters of oxygen produced at those conditions at 500 degrees Celsius, 175 kilopascals. So notice in this stoichiometry problem, we did a stoichiometry calculation first, and then followed that with a ideal gas calculation. Some problems, you have to do that in reverse. You might need to do an ideal gas calculation to begin with, then do a stoichiometry problem after that. All right, so let's try another gas stoichiometry problem. Question number 23 on the worksheet. Pause the video and see if you can do that yourself. So propane is burning, so to do any kind of stoichiometry problem, we need a balanced equation. So let's write a balanced equation. The propane C3H8, this is a hydrocarbon combustion reaction. The C3H8 is a hydrocarbon, and burning it is combustion, and so the products will be carbon dioxide and water vapor. And to balance, we'll have 3 carbon dioxides to balance carbons, 4 water molecules to balance the hydrogens, and 5 oxygens on the left to balance the oxygen atoms. Now we're looking for the mass of propane that could be burned if we use 50 liters of oxygen measured at 25 degrees in 1.20 atmospheres. So looking at the oxygen here, we know its volume, we know its temperature, and we know its pressure. So I don't know about you, but as soon as I recognize I know those 3 variables, I'm thinking of the ideal gas law. And if I know volume, pressure, and temperature for oxygen, then I know I can immediately calculate the moles of oxygen. If I calculate the moles of oxygen with the ideal gas law, then I can do a stoichiometry calculation to figure out the mass of propane that could be burned. So let's jump in with the ideal gas law. PV is nRT, and if we rearrange it, the moles of oxygen would be PV divided by RT. Notice how I put a little subscript beside moles to indicate that it's oxygen that I'm calculating. That's a pretty good idea. A lot of students don't do that, and then they forget what this moles refers to. They might think they're finding moles of propane, for example, and then just convert it to grams. So put a little subscript to label the moles. So our pressure is 1.20 atmospheres, and I can use atmospheres in the ideal gas law. That's okay. The volume was 50 liters. The value for R, the ideal gas constant, if I'm using atmospheres, R is 0.0821. And the temperature has to be in Kelvin, so 25 degrees, I just add 273, and I'll get 298 Kelvin. So grabbing a calculator, 1.2 times 50 divided by 0.0821 and divided also by 298 gives me 2.45 moles of oxygen. That's how many moles of oxygen we're using. So now we can rephrase the question. What mass of propane can be burned completely using 2.45 moles of oxygen? At this point, it's a basic stoichiometry problem like we had done in an earlier unit. We'll take the 2.45 moles of oxygen and set up 1 or 2 unit multipliers, I guess. First, we'll convert moles of oxygen to moles of propane using the balanced equation ratio, and then we can switch the moles of propane to grams using its molar mass. From the balanced equation, we can see that 1 mole of propane needed 5 moles of oxygen for combustion, and using a periodic table, the molar mass of propane 3 times carbon, so 3 times 12.01, plus 8 hydrogens, so 8 times 1.01, gives me a molar mass of 44.11 grams. So 2.45 moles divided by 5 times 44.11 tells me that I can burn 21.6 grams of propane using that oxygen gas. All right, so there's a stoichiometry problem where we first did an ideal gas law problem, then we followed it up with unit multipliers in stoichiometry. All right, in our third and final example of gas stoichiometry problems, take a look at number 25 here. Pause the video and see if you know what you're doing. All right, so zinc is being reacted with hydrochloric acid. So that sounds to me like a single replacement reaction. So zinc with hydrochloric acid. It's going to produce zinc chloride and hydrogen gas. The hydrogen gas is a Hofbrinkel element, so we'll put an H2. Zinc, when it becomes an ion, has a charge of 2+, and so it's going to bond with chloride, which has a charge of minus, and we'll get ZnCl2. And then to balance our equation, we'll put a 2 in front of the HCl. Now, when you read the question, did it jump out at you, number one, that this is a stoichiometry problem, right? So 35 grams of zinc is reacting with 8.2 grams of the hydrochloric acid, and we're asking for the volume of hydrogen gas produced, and then there's some conditions at the end. So does that sound to you like it's a stoichiometry problem? If this was a test, would you recognize that? Next, you see 35 grams of zinc and 8.2 grams of the hydrochloric acid. Does it strike you that when you know two masses of the two reactants, this is a limiting reagent stoichiometry problem? One of those two reactants, the 35 grams of zinc or the 8.2 grams of acid, will get used up, and that reactant is the limiting reagent. We use that reactant, the one that gets used up, to determine how much product we can make. So the first step of this problem would be to determine which of these is limiting. So to figure that out, we take one of them, it doesn't matter which. I'll take 35 grams of zinc, and I'm going to go calculate how many grams of the acid do I need to react with this. And I'll compare that with how much acid we were told we have. So let's do that. We'll switch the grams of zinc to moles of zinc using its molar mass. Then with the balanced equation, moles of zinc, we can find moles of the acid, the hydrochloric acid. And then because the question gave us grams of acid, we'll switch the moles of acid to grams of acid. The molar mass of zinc, 65.39 grams. From the balanced equation, 2 moles of acid for 1 mole of zinc. And then the molar mass of the acid, 1 mole, 1.01 plus 35.45, 36.46 grams is the molar mass of the acid. So 35 grams of zinc divided by 65.39, this gives me moles of zinc, times by 2, this gives me moles of acid, and times that by 36.46 gives me grams of acid. So we need 39 grams of acid is needed to use up all of our zinc. Do we have 39 grams of acid? Well, up in the question, we were told we have only 8.2 grams of acid, right? So since we have only 8.2 grams of acid, it's going to run out. We don't have enough acid. So the acid is the limiting reagent. The limiting reagent is the reactant that runs out first. So now that I know the acid is the limiting reagent, we'll start with that in another stoichiometry problem. We'll take the 8.2 grams of acid. Now we're wondering what volume of hydrogen gas can be collected. So we're going to take the grams of acid and we'll go calculate how many moles of hydrogen gas can be produced. Then we'll do an ideal gas law problem, but there's another wrinkle in there. I'm not sure if you noticed that. We'll talk about that in a moment. So let's go find how many moles of the hydrogen gas would be produced. You can pause and do that yourself if you haven't already. So we'll get rid of grams of acid, switch to moles of acid, and then moles of acid, switch to moles of hydrogen gas. The balanced equation, 1 mole of hydrogen gas for 2 moles of acid, and then the molar mass of our acid was 36.46 grams. So 8.2 divided by 36.46, 36.46, and then divided by 2, we can keep 3 significant digits, so this is 0.112 moles of hydrogen gas being produced. So now we want the volume. Well, looking at the question, we know the temperature, it's in Celsius, so that's going to have to go to Kelvin. We know the pressure, or do we? Well, look at this. The hydrogen gas is being collected over water. Why is that significant? Because if it's being collected over water, it means that in addition to hydrogen gas, there's going to be a little bit of water vapor mixed in with the hydrogen. So when we say that the pressure is 745 torr, if you look at that, 745 torr, that pressure would be the total pressure. So what we need to do is calculate the pressure of just the hydrogen gas by itself. Since that total pressure, 745 torr, is the hydrogen plus the water, that's Dalton's law, right? The total pressure is the sum of the pressures that make up the total. We're just going to subtract water's vapor pressure, which we're told in the question, from the total pressure. So we can say that the pressure of the hydrogen is 745 minus 21.1. So 745 minus 21.1, that's going to be 724 torr. Okay, there's the pressure of the hydrogen. We got that using Dalton's law, total pressure minus the water vapor pressure. Now let's convert that to either atmospheres or kilopascals. So I'll take my 724 torr, and I'll convert torr to atmospheres maybe. 1 atmosphere is 760 torr, so 724 over 760, we have 0.953 atmospheres is the pressure of hydrogen. So now I know the pressure of the hydrogen, I know the temperature of the hydrogen, I know the moles of the hydrogen. We can calculate the volume of the hydrogen using ideal gas law. PV is nRT, so the volume of the hydrogen would be N of hydrogen times RT over the pressure of the hydrogen. So that's going to be 0.112, the moles of hydrogen. Since we're using atmospheres, our R value is 0.0821. The temperature switched into Kelvin, 273 plus 23 is 296 Kelvin. And then the pressure of the hydrogen is 0.953 atmospheres. So the volume, 0.112 times 0.0821 times 296 divided by 0.953, the volume of the hydrogen is going to be 2.86, 3 significant digits, liters. Okay? So that question is about as hard as you can get, right, for a gas stoichiometry question. It was a limiting reagent problem. We had to figure out that the hydrochloric acid was limiting. Then we had to do a stoichiometry problem. With the limiting reagent, we found how many moles of hydrogen would be produced. In addition to that, we had to do some Dalton's law. We had to take the water vapor pressure away from the total pressure to get the hydrogen's pressure by itself, since the gas was collected over water. Then we did an ideal gas law problem and calculated the volume of hydrogen produced. So that's about as hard as you can get in gas stoichiometry. So we've just seen 3 gas stoichiometry problems. You can see they incorporate questions from basic stoichiometry and all the way up to limiting reagents. We didn't look at one, but there could also be a percent yield calculation involved here. Remember percent yield? And sometimes we have to collect gases over water. We use Dalton's law as well and the water vapor pressures. And we almost always will use ideal gas law somewhere in the problem, either at the beginning, like we saw in the last question, or at the end, like we did here. So you kind of have to read the question, play with it, and figure out as you go which of those scenarios you're dealing with. Is it a stoichiometry problem? If it is it a simple stoichiometry question, or is it a limiting reagent question? Where will I use the ideal gas law, at the beginning or the end? Is there water involved? Is the gas being collected over water? Those are all things you have to consider when doing gas stoichiometry problems. Good luck.